Imagine if I told you our solar system was initially meant to have another planet, one that never actually formed. For centuries, astronomers believed that there had to be a world between Mars and Jupiter, based on mathematical calculations. When they looked, they found something completely unexpected instead. Join me on a journey to discover how this search transformed our entire understanding of how planets form, as we explore 9 of astronomy's greatest mirages and the genuine breakthroughs they inspired. Tracking down these ghost worlds isn't just a quirky footnote. It's a theme that runs through the history of astronomy. Over the years, scientists have pursued predictions of planets, only to find nothing. Yet each anomaly, each setback, and each correction brings us closer to the truth. These cosmic ghosts drove innovation, refined our tools, and broadened our understanding of the solar system, even in their absence. Today, we're still searching for unseen worlds, fueled by the same curiosity. These cosmic mysteries remind us that science often progresses not just through answers, but through our willingness to question. Hey everyone, thanks for tuning in. Before we begin, just a quick housekeeping note. If you enjoy what I'm doing, a like and subscribe would be really helpful. It goes a long way in keeping the channel going. And don't forget to drop a comment. I'd really love to know what you think. Imagine a world that hit our own with such force it created the moon. This is not science fiction, but a leading scientific theory that answers one of astronomy's long-standing questions. For centuries, the origin of the moon has puzzled scientists. Early theories included capturing a passing body or having the moon form alongside Earth from the same material. However, these ideas couldn't explain the moon's unique characteristics and composition. The capture theory failed to account for the moon's stable orbit, while the co-formation theory couldn't explain why the moon has so little iron compared to Earth. The real breakthrough came when scientists analyzed lunar samples brought back by the Apollo missions. They found something unexpected. While the moon has much less iron than Earth, its oxygen isotope ratios are almost identical to Earth's. This created a paradox. If the moon formed elsewhere, its isotopes should differ. If it formed from the same material as Earth, it should have similar iron content. This isotopic similarity, despite compositional differences, became the key puzzle that needed solving. In the 1970s, scientists proposed the giant impact hypothesis. They suggested a Mars-sized protoplanet, later named Theia, collided with the early Earth. This enormous impact would have vaporized both bodies, sending debris into orbit around Earth. Most of Theia's dense iron core would have merged with Earth's core, while the lighter mantle material from both bodies formed a debris ring. From this ring, the moon gradually coalesced over millions of years. This explains both the isotopic similarities and the iron deficiency observed on the moon today. The impact theory also accounts for other characteristics of the Earth-Moon system. Earth's 23.5-degree axial tilt, which gives us our seasons, may result from this colossal collision. The moon's orbit also shows peculiarities that align with this violent origin story. Initially, the moon would have formed much closer to Earth and has been gradually moving outward ever since due to tidal interactions. Scientists have refined the model over decades. High-energy impact simulations indicate that a glancing blow, rather than a direct collision, would best explain the current system. More recent research proposes the synestia concept, where the impact created a temporary donut-shaped cloud of vaporized rock that eventually cooled to form both Earth and the Moon. Some researchers suggest that multiple minor impacts occurred rather than one giant collision, resulting in several moonlets that ultimately merged. Others propose that Earth had two moons initially that later combined. The search for evidence continues through lunar geology and advanced computer modeling. Scientists study subtle variations in lunar rock compositions, looking for traces of Theia's original material. They analyze the moon's internal structure using seismic data and gravitational mapping. Computer simulations have become increasingly sophisticated, allowing researchers to test different impact angles, speeds, and compositions. Even without direct evidence of Theia's remains, the hypothesis has profoundly advanced planetary science. It demonstrated how giant impacts shaped the early solar system and influenced the characteristics of the planets. The research has applications for understanding exoplanet systems and their formation histories. The search for Theia continues to drive technological innovation in both space exploration and computational astrophysics. This missing world, whether we ever find physical evidence of it or not, has provided crucial insights into how planets form and evolve. Theia's hypothetical existence explains not just our moon, but fundamental processes that shaped all planetary systems. The ongoing investigation reminds us that sometimes the most important discoveries come from pursuing explanations for what appears to be missing rather than what we can directly observe. What happens when mathematics predicts a world that doesn't exist? This isn't a philosophical question, but a real historical episode that fundamentally changed our understanding of physics. In the 19th century, astronomers noticed something peculiar about Mercury's orbit. The planet's perihelion, its closest point to the Sun, was gradually shifting in a way Newton's laws of gravity couldn't explain. This orbital precession amounted to about 43 arcseconds per century, which existing physics couldn't account for. Urbain Le Verrier, the French mathematician who had famously predicted Neptune's existence through orbital calculations, turned his attention to this Mercury problem. Having successfully used Newtonian mechanics to find a missing planet before, he applied the same methodology. In 1859, Le Verrier proposed that the discrepancies in Mercury's orbit could be explained by an undiscovered planet orbiting inside Mercury's path. He named this hypothetical world Vulcan, after the Roman god of fire and forging. The scientific community embraced this explanation because it followed the same successful pattern as Neptune's discovery. Astronomers across Europe and America began searching for Vulcan, particularly during solar eclipses when the sun's glare would be reduced. Amateur astronomers joined the hunt, and soon reports of sightings started to emerge. Some observers claimed to see dark spots transiting across the sun's surface, which they believed to be Vulcan passing between Earth and the sun. Dozens of claimed observations accumulated over the following decades, but none could be consistently verified. Different observers reported different orbital periods and positions. Some sightings turned out to be sunspots, while others were likely minor asteroids passing near Earth. The most promising observation came in 1878, when two experienced astronomers during a solar eclipse reported seeing a small planet near the sun, but subsequent searches during other eclipses found nothing in that location. The mystery persisted for over 50 years, despite extensive searching with increasingly powerful telescopes. The scientific community remained divided, with some maintaining faith in Vulcan's existence while others grew skeptical. The problem became more puzzling because if Vulcan existed, it should have been clearly visible during total solar eclipses. Yet no consistent evidence emerged, and the mathematical problem of Mercury's orbit remained unsolved. The solution arrived not from finding a new planet, but from a fundamental revolution in physics. In 1915, Albert Einstein published his theory of general relativity, which described gravity not as a force, but as the curvature of space-time caused by mass and energy. When Einstein applied his equations to Mercury's orbit, they perfectly accounted for the 43 arcseconds of unexplained precession. The mathematics showed that Mercury's path was affected by the sun's enormous mass, warping the space-time around it. This curvature causes Mercury to follow a slightly different path than Newtonian physics would predict. The effect is most noticeable for Mercury because it's the planet closest to the Sun, where space-time curvature is most pronounced. Einstein's calculations provided exactly the right amount of orbital deviation without requiring any additional planets. This was one of the first major validations of general relativity and demonstrated its superiority over Newtonian mechanics for describing extreme gravitational environments. Vulcan's non-existence revealed the limitations of Newtonian physics when applied to strong gravitational fields. The search for this phantom world ultimately helped usher in Einstein's revolution in physics. It showed that sometimes the solution to a scientific anomaly isn't finding new objects within existing theories, but recognizing when those theories themselves need revision. This episode demonstrates how scientific progress often comes from paying attention to minor discrepancies that don't fit established models. The Vulcan story became a cultural touchstone in both science and popular culture. It influenced everything from astronomy textbooks to science fiction, with Vulcan appearing as a fictional planet in various works. More importantly, it taught scientists a valuable lesson about scientific paradigm shifts. Sometimes what seems to be missing from our observations is actually pointing towards something missing from our understanding. This phantom world's legacy continues in modern astronomy. The meticulous search for Vulcan helped develop better observational techniques and more rigorous standards for confirming planetary discoveries. The episode also serves as a cautionary tale about confirmation bias, showing how scientists can sometimes see what they expect to see rather than what actually exists. The resolution of the Vulcan mystery represents one of the most critical transitions in scientific thinking. It marked the shift from classical Newtonian mechanics to Einstein's relativistic universe. This change wasn't just about replacing one set of equations with another. It represented a fundamentally new way of understanding space, time, and gravity. The search for a missing planet ultimately revealed that our entire framework for understanding the universe needed to be expanded. Vulcan's story reminds us that scientific progress often comes from investigating anomalies rather than confirming expected results. The most valuable discoveries sometimes emerge from following the evidence toward unexpected conclusions, even when those conclusions challenge our most fundamental assumptions about how the universe works. Why does our solar system lack the most common type of planet in the galaxy? This question emerged as astronomers began discovering thousands of planets around other stars. Exoplanet surveys revealed a surprising pattern. Super-Earths, planets with masses between Earth and Neptune, appear to be the most common type throughout the galaxy. These worlds typically range from about 2 to 10 times Earth's mass and often orbit close to their parent stars. Their abundance suggests they form easily under normal planetary formation conditions. Yet our solar system contains nothing in this size range between Mercury's orbit and the asteroid belt. This absence represents a significant gap in our planetary lineup that requires explanation. The discovery of this missing category of planets came primarily from transit surveys and radial velocity measurements. Space telescopes have identified numerous planetary systems where super-Earths orbit within what would be Mercury's orbit in our solar system. These planets often appear in compact systems with multiple worlds orbiting closer to their star than Venus orbits our Sun. Statistical analysis of these discoveries confirms that super-Earths are not just common, but actually represent the typical outcome of planet formation around other stars. This makes our solar system's architecture appear unusual rather than standard. The Grand Tack model offers one compelling explanation for this anomaly. This theory proposes that Jupiter underwent significant migration during the early solar system's formation. According to this model, Jupiter initially migrated inward toward the Sun due to interactions with the protoplanetary disk. This inward journey would have scattered or consumed much of the material that might have formed super-Earths in the inner solar system. Jupiter's gravitational influence would have cleared a path through the region where these planets typically form around other stars. Jupiter's migration didn't stop at the inner solar system. The model suggests Saturn's formation and subsequent migration created a gravitational interaction that pulled Jupiter back outward. This reversal of direction explains why Jupiter now orbits where it does, rather than closer to the Sun. The combined effect of Jupiter moving inward then outward would have dramatically altered the distribution of planetary building materials. This sweeping motion prevented the accumulation of sufficient material to form super-Earths in the inner solar system. This migration pattern accounts for several unique features of our planetary system. The inner planets are both small and widely spaced compared to many exoplanet systems. Mercury, Venus, Earth, and Mars all formed from the limited material that remained after Jupiter's passage. Their orbits maintain significant separation rather than clustering closely together. The asteroid belt exists in a region where Jupiter's gravity prevents planet formation through orbital resonances. These characteristics align with what we would expect from Jupiter's proposed migration history. Other planetary systems show markedly different architectures from ours. Many contain multiple super-Earths orbiting much closer to their stars than Mercury orbits the Sun. These planets often exhibit orbital periods measured in days rather than months or years. Their orbits frequently show resonances where planets complete orbits in simple integer ratios. Some systems contain several super-Earths, all orbiting within a distance equivalent to Mercury's orbit in our solar system. These compact, densely packed systems appear to be the norm rather than the exception throughout the galaxy. Our solar system's architecture may represent an unusual outcome of planetary formation. The Grand Tack scenario suggests that gas giant migration patterns, such as Jupiter's, might be less common than previously thought. Most planetary systems might form without such dramatic migratory events, allowing super-Earths to develop naturally in the inner regions. Alternatively, other systems might experience different migration patterns that produce various architectural outcomes. The diversity of exoplanet systems demonstrates that many pathways exist for planetary system formation. The absence of super-Earths in our solar system may have been crucial for Earth's habitability. Super-Earths typically have strong gravitational influences that could destabilize the orbits of smaller planets. Their presence might have prevented Earth from maintaining a stable orbit within the habitable zone. These massive planets often have thick atmospheres and extreme surface conditions unsuitable for life as we know it. their gravitational dominance might have prevented the formation of smaller, rocky planets like Earth and Mars. Our solar system's range of planetary sizes reveals essential insights into how planetary systems evolve differently. The same physical processes that operate throughout the galaxy produced different outcomes here due to specific conditions and events. Jupiter's migration created a unique environment that allowed small, rocky planets to form in widely separated orbits. This configuration may be relatively rare compared to the more common super-Earth systems found around other stars. The study of these missing planets helps us understand planetary formation mechanisms more broadly. It demonstrates how giant planets can sculpt entire planetary systems through their gravitational influence. The absence of super-Earths in our system provides a natural control case for comparing different planetary formation scenarios. This comparison enables astronomers to identify the factors that most significantly influence the final architecture of planetary systems. This investigation into what might have been but never formed in our solar system continues to yield valuable insights. As we discover more exoplanet systems, we gain a better statistical understanding of what constitutes a typical planetary system. Our solar system's unusual characteristics help us appreciate the diversity of possible outcomes from planetary formation processes. The missing super-Earths represent not just an absence, but an opportunity to understand why our planetary home developed its particular configuration. How did Mars turn into two distinct worlds in one? The red planet presents us with one of the most striking geological puzzles in our solar system. Take a look at any elevation map of Mars, and you immediately notice the dramatic split between the hemispheres. The northern lowlands appear smooth and surprisingly flat, while the southern highlands stand elevated and heavily cratered. This division isn't subtle. The average elevation difference measures about 6 kilometers between these two regions. This Martian dichotomy represents one of the planet's most fundamental characteristics, a feature that has intrigued planetary scientists for decades. The contrast between these two hemispheres suggests something dramatic happened early in Mars's history. The southern highlands show evidence of being ancient terrain, pockmarked with impact craters that testify to billions of years of bombardment. The northern lowlands present a completely different story. They appear much younger, with fewer impact craters and evidence of having been resurfaced by volcanic activity or other processes. This isn't just a slight variation in landscape. It's as if two different planets were stitched together along an irregular boundary. The giant impact scenario offers a compelling explanation for this dramatic division. In 2008, researchers proposed that a massive body between 1,600 and 2,700 kilometers across struck Mars during its early formation period. This impact would have been catastrophic, occurring around the same time frame as the theorized Theia impact that formed Earth's moon. The colliding body would have been substantial enough to alter Mars's surface and internal structure dramatically. This single event could explain why the planet shows such a stark division between its two hemispheres. This enormous impact would have created the massive Borealis Basin that now dominates Mars's northern hemisphere. The basin covers approximately 40% of the planet's surface, making it the largest known impact structure in our solar system. Its formation would have excavated enormous amounts of material, leaving behind a vast depression that became the northern lowlands. The impact's violence would have vaporized surface materials and fundamentally altered the planet's crustal structure. The basin's sheer size suggests an impact of almost unimaginable force during the solar system's early chaotic period. Spacecraft data from Mars orbiters provides compelling evidence supporting this giant impact hypothesis. Topographical mapping missions have precisely measured the elevation differences between the northern and southern hemispheres. These maps reveal the sharp boundary that separates the two regions, consistent with what we might expect from a massive impact event. Gravity measurements show variations that align with the impact scenario, indicating differences in crustal thickness between the impacted north and undisturbed south. Some observations even suggest possible remnants of what could be the ancient rim of the Borealis Basin. The evidence extends beyond simple elevation measurements. Geological mapping shows different rock compositions and ages between the two hemispheres. The northern plains contain evidence of extensive volcanic resurfacing that occurred after the hypothetical impact. Magnetic field measurements reveal patterns that suggest the impact may have disrupted Mars's early magnetic field. Thermal measurements show differences in how the two hemispheres retain and release heat. Multiple lines of evidence converge to support the idea that something dramatic and violent shaped Mars's northern regions. Alternative explanations propose that internal processes could have created the dichotomy. Some scientists suggest mantle convection might have caused variations in crustal thickness. This process involves the slow movement of the planet's interior due to heat transfer, which could theoretically create elevation differences. Other proposals include large-scale tectonic processes or even multiple smaller impacts rather than one giant collision. However, these alternative theories struggle to explain the sharp boundary and the specific geological features we observe. The impact hypothesis remains the most comprehensive explanation that accounts for multiple observed characteristics. The giant impact theory mirrors other violent early solar system formation events we've discussed. Enormous collisions and planetary scale impacts characterized our solar system's early history. The Theia impact that may have formed our moon represents a similar scale event. The late heavy bombardment period saw numerous significant impacts throughout the inner solar system. Mars's proposed impact fits within this context of a violent, chaotic early solar system, where giant collisions were not uncommon, but instead represented normal planetary formation processes. This possible impact may have determined Mars's climate evolution and potential for life. The collision would have released enormous energy, potentially vaporizing surface materials and injecting gases into the atmosphere. This could have created temporary periods of warming, followed by long-term cooling effects. The formation of the Borealis Basin might have created conditions suitable for an ancient northern ocean. Changes in the planet's rotation or axial tilt could have affected climate patterns and seasonal variations. The impact might have influenced whether Mars could maintain liquid water on its surface, a crucial factor for potential habitability. The search for evidence of Mars's impactor continues to drive planetary geology studies. Scientists are analyzing data from current orbiters and rovers in search of further evidence. They're examining the composition of rocks in the boundary region between the hemispheres and using computer simulations to model different impact scenarios, aiming to identify which one best matches the observed features. The search also includes looking for evidence of the impactor's composition in Martian meteorites that have reached Earth. Each new mission to Mars provides more data that helps refine our understanding of this possible catastrophic event. Future missions will focus on detailed mapping of the Borealis Basin and analysis of its geological features. Scientists aim to gain a deeper understanding of the proposed impact's timing in relation to other events in Martian history. They seek evidence of how the impact affected volcanic activity and internal heat flow. The relationship between the impact and the loss of Mars's magnetic field remains an active area of research. Each piece of evidence helps build a more complete picture of how this event shaped the planet's evolution. The ongoing investigation into Mars's two-faced nature demonstrates how planetary scientists reconstruct ancient events from modern observations. The search for the missing impactor shows how scientists use multiple lines of evidence to test hypotheses about events that occurred billions of years ago. This research helps us understand not just Mars's history, but the general processes that shape planetary evolution throughout the universe. The investigation continues as we gather more data from orbiting spacecraft and surface rovers. What happens when a mathematical pattern predicts a world that doesn't exist? This question lies at the heart of one of astronomy's most enduring searches. In the mid-18th century, Prussian scientist Johann Daniel Tyche noticed something interesting about the arrangement of planets. He observed that their distances from the Sun seemed to follow a mathematical sequence, starting with 0, 3, 6, 12, 24, and doubling each term, then adding 4 and dividing by 10. The resulting numbers roughly matched the known planetary distances in astronomical units. This pattern gained wider recognition when Johann Elert Bode promoted it in 1772, becoming known as the Tyche-Bode law. Following the 1781 discovery of Uranus, the law's credibility received a significant boost. The planet's distance closely matched the pattern's prediction, suggesting that the mathematical relationship might reflect some fundamental organizing principle of the solar system. This success led European astronomers to organize a systematic search for what they believed must be a missing planet between Mars and Jupiter. German astronomer Franz Xaver von Zach spearheaded this coordinated effort, convinced that the pattern indicated a real planetary body waiting to be discovered. It appeared to be a remarkable breakthrough in 1801 when Giuseppe Piazzi found Ceres, precisely 2.77 astronomical units from the Sun. This distance matched the Tyche-Bode prediction almost exactly, seemingly confirming the law's validity. Astronomers hailed this as a triumph of mathematical prediction, believing they had discovered the missing planet that completed the solar system's neat arrangement. The discovery seemed to show that the solar system followed strict mathematical rules governing the spacing of planets. This initial excitement grew with subsequent discoveries in the same region. Astronomers found Pallas, then Juno, and later Vesta, all orbiting at similar distances from the Sun. These discoveries initially reinforced the pattern, suggesting perhaps multiple small planets occupied the predicted orbital position. Each new finding appeared to strengthen the case for the Tyche-Bode law as a legitimate description of solar system architecture. The pattern seemed to be revealing itself through these successive discoveries. However, a problem gradually emerged as more objects were found. Instead of one planet, astronomers kept discovering numerous small bodies in the same region. These weren't fragments of a single world, but independent objects with their own orbits. The broken planet hypothesis emerged to explain this situation, suggesting these were pieces of a larger planet that had somehow been destroyed. This theory attempted to reconcile the mathematical prediction with the growing number of small bodies being discovered. The broken planet theory faced significant challenges as more data accumulated. By the mid-19th century, dozens of asteroids had been discovered, yet their total combined mass amounted to less than 5% of our moon's mass. If these were fragments of a shattered planet, the original world would have been extraordinarily small, much smaller than any known planet. The available mass simply didn't support the idea of a substantial planet having existed and then been destroyed in that location. The real explanation emerged from understanding Jupiter's gravitational influence. The gas giant's enormous mass creates orbital resonances throughout the asteroid belt region. These resonances, known as Kirkwood gaps, occur at specific distances where Jupiter's gravitational pull destabilizes orbits. At these distances, any material trying to accumulate into a larger body gets scattered by Jupiter's periodic gravitational tugs. These gaps represent regions where the orbital periods of asteroids become simple fractions of Jupiter's orbital period, leading to regular gravitational perturbations. Jupiter's influence prevents planet formation through several mechanisms. The resonances clear out material from specific orbital distances, creating gaps in the asteroid distribution. The giant planet's gravity also increases the relative velocities of asteroids, making gentle collisions that could lead to accretion less likely. Instead of sticking together, colliding asteroids tend to fragment or bounce off each other. This combination of effects maintains the asteroid belt as a collection of small bodies rather than allowing them to coalesce into a single planet. Modern space missions have transformed our understanding of asteroids. Missions to Vesta and Ceres revealed these aren't fragments, but protoplanets that began forming but never completed the process. They represent planetary building blocks that were prevented from growing larger by Jupiter's influence. Other asteroid missions have shown that many asteroids are rubble piles, loose collections of material held together by gravity rather than solid fragments of a larger body. These observations confirm that asteroids are primordial objects, not debris from a destroyed planet. The Tyche law ultimately proved to be a numerological coincidence rather than a fundamental physical principle. While it correctly predicted Ceres and Uranus, it failed with Neptune and Pluto. Neptune's actual distance of 30 astronomical units and Pluto's 39 astronomical units bore no relation to the pattern's predictions. The law's successes were likely due to chance rather than any underlying physical mechanism governing planetary spacing. This failed prediction, nonetheless, led to significant scientific advances. The search for the missing planet spurred the first organized international astronomical collaboration. It drove improvements in observational techniques and telescope technology. Most importantly, it helped scientists understand how gravitational resonances shape solar system architecture. The investigation revealed how giant planets can create barriers to planet formation in certain regions. The asteroid belt story demonstrates the importance of empirical evidence over mathematical patterns. It shows how scientific understanding evolves through observation and testing of hypotheses. The search for a phantom planet ultimately yielded valuable insights into planetary formation processes and the dynamics of our solar system. It revealed how gravitational interactions can create permanent features in planetary systems. This investigation continues to inform our understanding of exoplanet systems. The principles learned from studying Jupiter's influence on the asteroid belt help explain architectural features observed around other stars. The recognition that giant planets can prevent planet formation in certain regions helps explain why some planetary systems show gaps or unusual spacing patterns. These insights contribute to our broader understanding of how planetary systems form and evolve throughout the galaxy. The asteroid belt's missing planet represents a case where a mathematical pattern pointed towards something that didn't exist physically, but led to a deeper understanding nonetheless. The search for this phantom world ultimately revealed more about the real processes that shape planetary systems than about any actual missing object. It demonstrates how scientific progress often comes from following intriguing leads, even when they don't lead where initially expected. How did ancient mythology become a modern doomsday prediction? This transformation occurred through a combination of speculative interpretation and modern anxiety. In 1976, Zecharia Sitchin published The 12th Planet, the first installment of his Earth Chronicles series. Sitchin claimed to have deciphered ancient Sumerian texts that revealed the existence of a hidden planet called Nibiru. According to his interpretation, this world followed a highly elliptical orbit around the Sun, completing one revolution every 3,600 years. He proposed that during its closest approach to the Sun, Nibiru would pass through the inner solar system between Mars and Jupiter. Sitchin's narrative extended beyond astronomy into creation mythology. He suggested that advanced beings, called the Anunnaki, inhabited Nibiru. These extraterrestrial visitors supposedly came to Earth approximately 450,000 years ago, seeking gold to repair their planet's atmosphere. According to Sitchin's interpretation, the Anunnaki genetically engineered early humans to serve as workers in their gold mines. This elaborate story reimagined Mesopotamian creation myths as accounts of extraterrestrial intervention rather than religious narratives. Scholars specializing in ancient Mesopotamian texts strongly criticized Sitchin's interpretations. Professional Assyriologists and archaeologists pointed out numerous errors in his translations of Sumerian cuneiform tablets. They emphasized that ancient Babylonian astronomy recognized only 5 planets visible to the naked eye, Mercury through Saturn, and never described a 12th planetary body. The academic consensus held that Sitchin's work represented speculative fiction rather than legitimate scholarship. His interpretations bore little resemblance to the actual content and context of the ancient texts he claimed to be translating. Despite scholarly rejection, Sitchin's ideas gained traction through the 1980s and 1990s. His books found an audience among readers interested in alternative history and ancient astronaut theories. The narrative resonated with people seeking explanations that challenged conventional understandings of human origins. This popularity established a foundation for the myth's later expansion into broader cultural awareness. Nancy Lieder significantly amplified the Nibiru narrative in the 1990s. She claimed to be in contact with extraterrestrials from Zeta Reticuli, who warned her about an approaching planetary threat. Lieder initially referred to this object as Planet X, but her followers quickly connected it with Sitchin's Nibiru. She predicted catastrophic events resulting from this planet's close approach to Earth, gaining attention through early internet forums and websites. Her claims represented a fusion of Sitchin's mythology with contemporary UFO and conspiracy theories. The internet provided the perfect environment for the Nibiru myth to spread and evolve. Websites and forums allowed believers to share information and reinforce each other's convictions. YouTube videos presented alleged evidence of Nibiru's approach, often using manipulated images or misidentified celestial objects. Conspiracy theories emerged, claiming that NASA and other space agencies were hiding the truth about the approaching planet. This online ecosystem enabled the myth to reach audiences far beyond Sitchin's original readership. The Nibiru narrative became intertwined with the 2012 phenomenon centered around interpretations of the Mayan calendar. Some proponents claimed that the Mayan long count calendar's end date of December 21, 2012, predicted the arrival of Nibiru and a resulting global catastrophe. This connection amplified public concern and media attention. The combination of ancient prophecy and modern astronomical speculation created a powerful narrative that resonated with apocalyptic fears. NASA received thousands of inquiries from concerned citizens, including children worried about the predicted doomsday. Astronomers repeatedly explained that no such planet existed or could approach undetected. They pointed out that an object large enough to cause a global catastrophe would have been visible to amateur astronomers for years before its closest approach. Professional surveys, like the Wide Field Infrared Survey Explorer, had scanned the entire sky without detecting any such planetary body. The scientific evidence consistently contradicts the Nibiru predictions. When December 21, 2012, passed without incident, proponents simply adjusted their predictions rather than abandoning the belief. New dates were proposed, and the narrative continued to evolve. This pattern demonstrates how conspiracy theories and pseudoscientific beliefs can persist despite contrary evidence. The flexibility of the narrative allowed it to survive factual disconfirmation. The Nibiru myth entered mainstream popular culture through various media representations. It appeared in novels, documentary-style YouTube videos, and even influenced Hollywood productions. While these representations often took creative liberties with the original mythology, they helped maintain public awareness of the concept. This cultural penetration demonstrates how pseudoscientific ideas can gain legitimacy through repeated exposure in entertainment media. From a psychological perspective, the Nibiru myth's persistence reveals several human tendencies. The narrative appeals to pattern recognition, the human inclination to see meaningful connections where none exist. It also taps into apocalyptic thinking, a recurring theme throughout human history. The conspiracy elements reflect distrust of authorities and institutions. The story provides a simple explanation for complex phenomena, offering certainty in an uncertain world. Astronomically, Nibiru's proposed orbit presents numerous problems. A body with a 3,600-year period would have an extremely elongated elliptical path. Such an orbit would be dynamically unstable over geological timescales due to gravitational interactions with other planets. Any object on this trajectory would likely have been ejected from the solar system billions of years ago. The gravitational effects of a massive planet passing through the inner solar system would disrupt the orbits of other planets, creating observable anomalies that simply don't exist. The Nibiru phenomenon serves as a case study in how misinformation spreads in the digital age. It demonstrates how ancient mythology can be repurposed for modern concerns. The narrative's persistence shows how emotional appeals can outweigh factual evidence for some audiences. It reveals the challenges scientists face when communicating with the public about complex topics. This phantom world story ultimately tells us more about human psychology than planetary science. It shows how people seek meaning and pattern in random events. The narrative fulfills emotional needs for drama, significance, and alternative explanations. While Nibiru doesn't exist as a physical world, it represents a real phenomenon in how humans process information and construct beliefs. The ongoing belief in Nibiru, despite overwhelming contrary evidence, illustrates the power of confirmation bias. People tend to accept information that supports their existing beliefs while dismissing contradictory evidence. This cognitive tendency helps explain why the myth continues to find new adherents even after repeated failed predictions. The narrative provides a framework that reinforces itself through selective attention to supporting claims while ignoring disconfirming evidence. The scientific response to Nibiru claims has helped improve public communication about astronomy. NASA and other organizations have developed better strategies for addressing pseudoscientific beliefs. They've created educational resources that explain how we know particular celestial objects don't exist. This effort represents an essential aspect of modern scientific outreach and education. The Nibiru story continues to evolve with new technological developments. Each generation of telescopes and surveys provides more comprehensive sky coverage, making it increasingly unlikely that large unknown planets exist within our solar system. Yet the myth persists, adapting to new contexts and finding new expressions. This demonstrates the enduring human capacity for imagination and storytelling, even when those stories conflict with established scientific understanding. The search for this phantom world ultimately reveals our deep need to find patterns and meaning in the cosmos, whether those patterns actually exist or not. How does the success of one prediction spark generations of searching? The discovery of Neptune in 1846 through mathematical prediction set a powerful template that would drive astronomical research for over a century. When astronomers observed irregularities in Uranus's orbit, they used mathematical calculations to determine the position and mass of an unseen planet, demonstrating that mathematics could reveal hidden celestial bodies. This triumph of Newtonian mechanics established a compelling precedent that inspired subsequent searches for other hypothetical planets. The success created a belief system where orbital anomalies automatically suggested undiscovered worlds, setting in motion a scientific quest that continues to this day. Percival Lowell became the most dedicated proponent of this mathematical approach to planet hunting. Inspired by Neptune's discovery, he established Lowell Observatory in 1894 specifically to search for what he termed Planet X. Lowell spent years calculating the supposed planet's characteristics based on perceived irregularities in the orbits of Uranus and Neptune. He published detailed predictions in 1905 and 1915, estimating Planet X would be several times Earth's mass. Lowell meticulously photographed the sky, searching for this unseen world until he died in 1916, leaving behind both his calculations and his unfinished search. The search continued under Clyde Tombaugh, who joined Lowell Observatory in 1929. Using a blink comparator to examine photographic plates of the same star field taken days apart, Tombaugh looked for moving objects against the background stars. His systematic survey paid off on the 18th of February 1930 when he discovered Pluto near the position Lowell had predicted. The timing seemed perfect. The announcement came on the 149th anniversary of Uranus's discovery. Initially, astronomers believed they had found Lowell's Planet X, completing the pattern established by Neptune's discovery. However, problems with this identification soon emerged. Pluto's mass measured only about 0.2% of Earth's mass, far too small to account for the gravitational effects Lowell had calculated. As telescopes improved, astronomers realized Pluto was just one of many similar-sized objects in the outer solar system. The supposed perturbations in Neptune's orbit that had inspired Lowell's calculations didn't match what improved observations revealed. The mystery deepened as better data failed to support the original premise of a massive unknown planet. The final blow to Lowell's Planet X hypothesis came from the Voyager 2 spacecraft's 1989 flyby of Neptune. By precisely measuring Neptune's gravitational influence on the spacecraft, scientists obtained an accurate mass measurement for the planet. When they incorporated this new mass into orbital calculations, the previously observed anomalies in Uranus's and Neptune's orbits disappeared. The mathematical need for Planet X vanished with improved data quality. This demonstrated how earlier calculations based on imprecise measurements had created a phantom problem that better instrumentation could resolve. Despite this resolution, the concept of an undiscovered planet persisted in revised form. In the 2010s, astronomers noticed something peculiar about distant Kuiper Belt objects. Several of these icy bodies exhibited unusual orbital alignments, suggesting gravitational influence from an unseen massive object. Their orbits clustered in ways that seemed statistically unlikely to occur randomly. This pattern prompted Konstantin Batygin and Mike Brown to propose the Planet 9 hypothesis in 2016. Unlike Lowell's calculations, this new hypothesis emerged from observational data rather than orbital anomalies of known planets. The Planet 9 hypothesis proposes a distant world with a mass about 10 times Earth's, orbiting hundreds of astronomical units from the Sun. This planet would follow a highly elliptical path that takes thousands of years to complete. Its gravitational influence would explain the clustered orbits of particular extreme trans-Neptunian objects. The hypothesis suggests this world formed in the early solar system and was subsequently scattered outward by gravitational interactions with Jupiter or Saturn. Unlike earlier Planet X theories, this proposal focuses on explaining specific orbital patterns rather than compensating for calculation errors. Modern astronomical surveys continue searching for this hypothetical planet using advanced technology. The Subaru telescope in Hawaii conducts systematic searches of the predicted orbital region. Its large aperture and wide field of view make it ideal for detecting faint objects in the distant solar system. The forthcoming Vera Rubin Observatory in Chile will dramatically accelerate this search with its unprecedented survey capabilities. These instruments represent the latest evolution in a long tradition of technological innovation driven by the search for unseen planets. The Planet X quest has consistently driven advancements in observational astronomy and survey methodology. From Lowell's photographic plates to Tombaw's blink comparator to modern digital surveys, each generation of technology has improved our ability to detect faint, distant objects. This technological progression demonstrates how the pursuit of specific scientific questions often yields broader benefits for the entire field. Even unsuccessful searches contribute valuable data and methodological improvements. The ongoing investigation illustrates how scientific questions evolve with new evidence and improved understanding. The original Planet X concept emerged from measurement errors and incomplete data. The modern Planet 9 hypothesis stems from precise observations of actual orbital patterns. This evolution shows how scientific inquiry adapts to new information while maintaining the fundamental drive to understand our solar system's structure. The question has shifted from explaining calculation errors to understanding legitimate orbital anomalies. This search demonstrates the dynamic nature of scientific investigation, where hypotheses must continuously adapt to new evidence. The transition from Lowell's mathematical predictions to modern observational astronomy represents a maturation of both techniques and understanding. Each failed hypothesis has led to improved methods and deeper insights into solar system dynamics. The process shows how science corrects itself over time while maintaining curiosity about unanswered questions. The Planet X story exemplifies how scientific research often follows paths that twist and turn with discoveries. What began as a search for a massive planet to explain calculation errors became a hunt for a small world that turned out to be part of a larger population. Now the search continues for a different kind of planet based on other evidence. This evolution demonstrates how scientific understanding progresses through continuous questioning and investigation, with each answer raising new questions worth exploring. What if a giant planet hid in the solar system's darkest reaches? This question drove the search for Tyche, a hypothetical world proposed to explain subtle patterns in comet behavior. The outer solar system contains the Oort cloud, a vast spherical shell of icy bodies extending tens of thousands of astronomical units from the Sun. Long-period comets originate from this distant region, following orbits that take thousands or even millions of years to complete. In the late 1990s, researchers noticed these comets weren't arriving from random directions, but showed slight clustering in their points of origin. This anisotropy suggested something might be gravitationally influencing their trajectories. The Tyche hypothesis emerged in 1999 when researchers proposed that a massive unseen planet could explain these orbital patterns. They suggested a gas giant between 1 and 4 times the mass of Jupiter, orbiting approximately 5,000 to 10,000 astronomical units from the Sun. At this tremendous distance, such a planet would be extremely faint and cold, making detection challenging with conventional telescopes. The researchers named this hypothetical world Tyche, after the Greek goddess of fortune, positioning it as a benevolent counterpart to the more destructive Nemesis hypothesis. The proposal represented a testable explanation for the observed comet clustering that didn't require invoking multiple random coincidences. This distant giant would exert gravitational influence on Oort cloud objects, gently nudging them toward specific orbital paths. As comets approached the inner solar system, their arrival directions would reflect this preferential nudging. The hypothesis calculated that a planet of this mass at this distance could create the observed anisotropy without disrupting the orbits of known planets. The mathematics showed the effect would be subtle but measurable over many comet observations. This made Tyche a plausible explanation within known physical laws, unlike some more speculative proposals. NASA's Wide Field Infrared Survey Explorer mission provided the perfect tool to test this hypothesis. Launched in 2009, WISE scanned the entire sky in infrared light, precisely the wavelength range where a cold, distant planet would be most visible. A Jupiter-sized object at thousands of astronomical units would emit faint infrared radiation due to residual heat from its formation billions of years ago. The survey's sensitivity and all-sky coverage made it capable of detecting such an object if it existed within the proposed parameters. Scientists specifically analyzed WISE data, looking for evidence of Tyche during the mission's operational period from 2009 to 2011. The survey collected enormous amounts of data, cataloging hundreds of millions of infrared sources across the sky. Researchers meticulously searched this database for objects matching Tyche's predicted characteristics. They looked for slow-moving point sources with specific infrared signatures that would indicate a cold planetary body. The search covered the entire celestial sphere, leaving no region unexamined. This comprehensive approach ensured that if Tyche existed within the proposed distance and mass range, it would have been detected. The results came as a definitive negative. After thorough analysis, no object matching Tyche's predicted properties appeared in the WISE data. The survey found no evidence of a Jupiter-sized planet within 10,000 astronomical units. This non-detection effectively ruled out the existence of Tyche as initially proposed. The hypothesis had made specific testable predictions, and the observations failed to support them. This outcome demonstrated the importance of empirical evidence in astronomical research, even for objects at the solar system's farthest reaches. The failure to find Tyche provided valuable information about the outer solar system's composition. It established upper limits on the size of possible undiscovered planets in the Oort cloud region. We now know that no gas giant exists within the surveyed volume, constraining future theories about solar system formation and evolution. This negative result helped refine our understanding of what kinds of objects might inhabit the distant solar system. It showed that while smaller objects might exist undetected, nothing of planetary mass remains hidden in that region. This investigation advanced our understanding of Oort cloud dynamics and comet origins. The observed anisotropy in comet arrivals required explanation, even without Tyche's existence. Researchers developed alternative theories involving galactic tides or passing stars to account for the clustering patterns. The search prompted more detailed modeling of how external gravitational influences affect Oort cloud objects. It led to improved understanding of how comets transition from the cloud's outer regions to orbits that bring them into the inner solar system. The Tyche search demonstrated the power of infrared astronomy in detecting cold, distant objects. WISE's success in ruling out a Jupiter-sized planet showed the capability of modern survey instruments. This technological demonstration has applications beyond solar system studies, informing the search for planets around other stars and faint objects throughout the galaxy. The methodology developed for this search now helps astronomers study other poorly understood regions of our solar system. The techniques continue to be refined for future surveys with even more sensitive instruments. This episode represents a classic example of how science progresses through testable hypotheses. The researchers proposed a specific, measurable prediction based on observed anomalies. They used available technology to test that prediction thoroughly. When the evidence didn't support the hypothesis, science advanced through the elimination of possibilities. The process yielded valuable insights even without confirming the original idea. It showed how negative results can be as scientifically sound as positive discoveries when properly obtained and analyzed. The Tyche hypothesis remains a historical case study in astronomical methodology. It illustrates how scientists develop testable explanations for observational anomalies. The episode demonstrates the importance of making specific, falsifiable predictions rather than vague claims. It shows how modern technology enables us to test ideas that would have been untestable just decades earlier. The story continues to inform how astronomers approach the search for unknown objects in our solar system's outer regions. This investigation into a world that wasn't there ultimately expanded our understanding of what actually exists in our solar system's farthest reaches. It helped establish boundaries and constraints that guide current research into trans-Neptunian objects and Oort cloud dynamics. The search contributed to our knowledge of how planetary systems form and evolve over billions of years. While Tyche itself never materialized, the pursuit of this phantom world yielded genuine advances in both observational techniques and theoretical understanding. Could our sun have a dark companion responsible for mass extinctions? This startling question emerged from a meticulous analysis of the Earth's geological record. In 1984, paleontologists David Raup and Jack Sepkoski published a statistical study of extinction events over the past 250 million years. Their analysis revealed a pattern suggesting major extinction events occurred approximately every 26 million years. This apparent periodicity included well-known catastrophes like the end Permian and end Cretaceous extinctions that wiped out most species on Earth. The regularity of these events suggested they might not be random occurrences, but instead driven by some recurring external trigger. The Nemesis hypothesis proposed a compelling mechanism to explain this 26 million year cycle. Researchers suggested the Sun might have an unseen stellar companion orbiting at a tremendous distance. This hypothetical object, named Nemesis after the Greek goddess of divine retribution, would follow an extremely elongated elliptical path around the Sun. Its orbital period would match the extinction cycle, bringing it close to the solar system every 26 million years. At its closest approach, Nemesis's gravitational influence would disturb the Oort cloud, sending showers of comets toward the inner solar system. The proposed characteristics of Nemesis aimed to explain why it hadn't been detected. Researchers suggested it might be a dim red dwarf, or even a brown dwarf, a failed star too small to sustain hydrogen fusion. Such an object would emit very little visible light, while still possessing significant mass. Its orbit would extend up to about 90,000 astronomical units from the Sun, far beyond the Kuiper Belt and deep into the Oort cloud region. At this distance, even a substantial object would be extremely difficult to detect with conventional telescopes. The mechanism involved precise gravitational interactions. As Nemesis approached perihelion, its gravity would perturb the orbits of icy bodies in the Oort cloud. This disturbance would send numerous comets on trajectories that could bring them into the inner solar system. Some of these comets would collide with Earth, causing environmental catastrophes that could trigger mass extinctions. The timing would correspond with the observed 26 million year cycle, providing a physical explanation for the statistical pattern. Testing this hypothesis required extensive sky surveys in both optical and infrared wavelengths. Initial searches in the 1980s and 1990s looked for faint stellar objects that might match Nemesis's predicted characteristics. These early surveys covered large portions of the sky, but lacked the sensitivity to detect extremely dim objects at great distances. The searches continued with the improvement of technology, but no convincing candidate emerged. The hypothesis faced growing skepticism as surveys failed to find evidence of the proposed companion. Statistical challenges emerged regarding the extinction periodicity itself. Subsequent analysis of the fossil record raised questions about whether the 26 million year cycle actually existed. Some researchers argued the pattern might be an artifact of how extinction events were dated or categorized. Others suggested alternative periodicities, or questioned whether the events were truly regular enough to require an external trigger. The statistical foundation of the hypothesis became increasingly uncertain as more data accumulated. Concerns about orbital stability presented another major problem. An object following such a wide, slow orbit would be vulnerable to gravitational perturbations from passing stars and the galactic tide. Over millions of years, these external influences would likely disrupt Nemesis's orbit, changing its period or even ejecting it from the solar system entirely. Maintaining a stable 26 million year orbit for hundreds of millions of years seemed statistically unlikely given the dynamic environment of the galactic disk. Modern infrared surveys provided the most comprehensive tests of the Nemesis hypothesis. The 2-micron all-sky survey scanned the entire sky in infrared light between 1997 and 2001. This survey was particularly sensitive to cool, dim objects like the proposed Nemesis. Later, the Wide-Field Infrared Survey Explorer conducted an even more sensitive all-sky study from 2009 to 2011. These missions cataloged countless objects, but found no evidence of a stellar companion matching Nemesis's predicted characteristics. The combined negative results from these surveys effectively ruled out the existence of Nemesis as initially proposed. No object with sufficient mass to significantly perturb the Oort cloud exists within the searchable volume around our solar system, while smaller, more distant objects might remain undetected. Nothing matching the specific requirements of the Nemesis hypothesis has been found. The search demonstrated that our solar system likely lacks such a companion. Despite its failure as a physical reality, the Nemesis hypothesis spurred valuable scientific research. It prompted more detailed studies of extinction periodicity and its potential causes. The search advanced our understanding of how to detect faint, distant objects through infrared astronomy. It also contributed to improved models of Oort cloud dynamics and how external influences affect comet orbits. The investigation into possible solar companions led to better constraints on what might exist in our solar system's outer reaches. The hypothesis also stimulated research into alternative explanations for extinction events. Scientists explored other periodic phenomena that might influence Earth's environment, such as galactic plane crossings or solar system oscillations. The investigation prompted more sophisticated statistical analysis of the fossil record and the timing of extinctions. It encouraged interdisciplinary collaboration between astronomers, paleontologists, and climate scientists studying catastrophic events. Nemesis's legacy continues in ongoing research about solar system dynamics and extinction causes. While the specific hypothesis has been discarded, the questions it raised remain relevant. Scientists continue to study how external influences might affect life on Earth over geological timescales. The investigation demonstrated how even incorrect hypotheses can drive scientific progress by motivating new observations and theoretical developments. The search for this phantom companion ultimately expanded our understanding of both celestial mechanics and Earth's biological history. The Nemesis story represents a fascinating example of how science sometimes follows intriguing possibilities that don't pan out but still yield valuable insights. It shows how statistical patterns can inspire physical hypotheses worth testing. The episode demonstrates the scientific process's self-correcting nature, where ideas must withstand observational testing and competing explanations. Although Nemesis doesn't exist, the investigation it prompted has contributed to multiple scientific fields and enhanced our understanding of cosmic influences on terrestrial life. These phantom worlds show how scientific progress stems from investigating anomalies. Every search, whether successful or not, fundamentally broadens our understanding of planetary science. The search for missing planets has driven technological innovation in telescopes and survey methods, while refining our grasp of orbital mechanics and the formation of the solar system. Even disproven hypotheses, such as Vulcan and Tyche, have yielded valuable insights that have advanced multiple scientific disciplines. The ongoing investigation reminds us that our cosmic neighborhood still holds mysteries waiting to be discovered through curiosity and rigorous observation. The universe continues to reveal its secrets to those willing to ask questions.